Okay, let's get into kinetics. Chapter 12 is kinetics. Chapter 13 is equilibrium. Now, historically speaking, the theoretical mathematical treatment of equilibrium came first. Chemical kinetics took a little more development, but understanding equilibrium is best done if you know something about kinetics first. So that's why we're taking kinetics before equilibrium. So what do we mean by kinetics? Anytime you hear the term kinetics, think of motion. Like kinetic energy of a particle, it has to be moving. And in this case, we're talking about changes in concentrations of either reactants or products. And I'll explain which one is preferred in just a minute. But we're talking about the rate of a reaction. Something is moving, and that's the case of where we're talking about a rate of reaction. And what we want is to quantify the change of concentration of any reactant or product. And in this case, we've represented it as A. And we want to know the concentration of this A, the final concentration minus the initial concentration. Right. Whenever we say delta, we mean final minus initial concentration of A. Divided by how much time did it take to go from this concentration to that concentration. So we need the final time minus the initial time. And that will give us our delta T. And these units can be in anything. They can be in seconds, they can be in minutes, hours, days. So some reactions take a very long time to proceed, some take a very short time. So these units are variable. When we put a square bracket around a concentration variable, we usually mean molarity. And that's the way we're going to treat it. So the concentration will change by so many molar per whatever time you look. Okay, so if we actually ran a reaction, in this case, we've got one reactant, nitrogen dioxide, is producing two products. Right, they're all gases. So the stoichiometry holds in terms of this reaction. If we start off with 0.01 molar, we begin at 0.01 molar, that means there's no product there to begin with. That's our time zero. Time zero. Then after 50 seconds, so this reaction is moving along pretty good clip. After 50 seconds, we have 0.0079 remaining of the nitrogen dioxide. And this is molar. So how much should we expect over here? Well, whatever disappeared over here should show up over there because it's a 1-to-1, 2-to-2, 1-to-1 ratio. So the difference here is 2-1. Yeah, 0.0021. So the concentration is beginning to increase in the products. And the ratio here is half of that, or half of this, whichever you prefer. So whatever disappeared over here has to show up over here. And this one is going to be half of that. limited by the number of significant figures we're allowed. Okay, so it's going to continue to do that. Whatever disappears over here shows up over there. And it doesn't have to be linear. In other words, if we go to 100, we usually, not, well, I can't say usually, sometimes it would be the same amount of jump from here to here as there. But in this case, it's not. 0065. Right? So the difference in concentration here is 0.0014, right? Yeah, 0.0014. And since these are additive, now the concentration over here is increased by this much, which means that this amount will be 0035. And this would have increased by 0007. So that means its value would be 0018. Okay, so I'm trying to orient you to how the data is recorded. And so we don't make a mess here. Now the rest of them we do the same way. Whatever disappears over here shows up over there, and it's additive. Okay, so we have this list of numbers, concentrations in molar units of measure. And we've watched this reaction for 400 seconds until, as you notice, as we get toward the higher values of time, the nitrogen monoxide and the oxygen actually exceed the amount of NO2 that's remaining. Okay, so that's an example of a data set, and it follows the stoichiometry of the reaction, of the balanced equation. This is a graphical representation. Everything's kind of small, so just pay attention to the direction of movement. Concentration is on the y-axis and time is on the x-axis. And you'll notice that the, let's see, I'll have to get close to the, is there more to that one? No, there's not. The NO2 concentration is the green line, starts up at 0.01 molar, and the products are at zero, at time zero. And they gradually increase. And notice that it's not a straight line relationship. They don't increase or decrease, as the case may be, by a linear progression. So we get this curve for each one of them. Now, if we want to know how fast the reaction is moving at any given time, we need what's called the slope of the tangent line. So if with a curve, you can have an instantaneous rate. Have you ever heard that term? Okay. So we just have a tangent to that line. So the slope at that position on the curve is actually the slope of this straight line. And it will change, right? As we go down here, the slope gets less and less and less. So this value changes depending on where you are in the progression of the reaction. Now, there are examples where the progression is linear. There are not very many of them, but you could get a straight line going this way and straight lines going that way. And we'll talk about that in more detail in just a few minutes. Okay, that's known as the instantaneous rate. It's the slope of the tangent to the curve. Okay, so we've defined what the rate is. Now, each reaction, we can express a rate law for the reaction. And we have two possibilities. We can either say the rate is related to the amount of reactant as it changes, or we can pick the products. We usually pick the reactant because if we start the reaction with only reactant, then we don't have competing return reactions to deal with. So what I'm saying is this reaction could be written with an arrow that way or that way. So it can, once you start building up product, you can get return reactions. So this rate law is usually expressed in terms of the initial amounts of the reactants. And we have a constant that's associated with the reactant, in this case, the reactant. And then we have some value in here. In this case, it's NO2, and it's raised to a power. This is known as the order. If there's only one term in this rate law, then that is the reaction order. If there's more than one term, and there can be, we could put another term. Say if we had a reaction where there were two reactants, then we could put both of them in here, and they would have individual orders, reactant orders. Okay. In this case, we have a value here raised to the power of this concentration and a different value here. Well, it doesn't have to be different, but we determine it by measuring it. These are empirically determined values. They cannot be derived from the balanced equation. And if we use these as the reactants under the very beginning, at the beginning of the reaction where there are no products, we call this initial rate. And that gives us the best approximation of how fast the reaction is. The way the reaction proceeds is best at the initial rate when you don't have a competing return reaction. Now, when we were looking at that previous expression for NO2, this rate law would be best expressed for the zero time or very small increments of time at the very beginning. Because as we move down that curve, the reason that the curve flattens out is because we're starting to get competing return reactions. And that flattens out the curve. Okay. Like I said before, these values are empirically determined. They're not derived from the balanced equation. Okay, there are two ways to express these rate laws. Before I go any further, the reaction order, if we have more than one term here, then the reaction order equals N plus M. It's just a summation of these values. That's reactant order. So I'm sorry. There we go. These are individual powers, and this is the summation of the availables. Okay, there are two ways to express a rate law. One is called the differential rate law, and it simply shows how the reaction rate depends on concentration. So this rate depends on these concentrations. Okay. So this would be the differential rate law. And these terms are derived from calculus. If you've ever been exposed to calculus, then these terms will be familiar. If not, then you'll just have to take my word for it. The other way to express the rate law is in an integrated form. And whenever I hear the word integrated, I always think, what's the area under a curve? But what the integrated rate law shows us, integrated rate law shows us the relationship the, excuse me, concentrations depend on time. So this would be something like this. That concentration depends upon time. See, this expression up here doesn't have a time factor in it. This one does. So it depends on how you want to solve the equation as to which one of these you use and what information are you given. If the approach is to introduce time factors, say, for instance, if I wanted to know the concentration of the reactant after so many minutes or seconds or whatever the units of measure are, then I would go to the integrated rate law because that introduces time factor. If I simply wanted to know what is the rate based upon the initial concentrations, then I would go to the differential rate law. But they're related. This one's derived from that one. So if you know one, you can derive the other one. Okay, so in summary, we consider the reactions only under conditions where the reverse reaction is unimportant. That's initial rates. That's the easiest way to investigate the kinetics of a given reaction. And we're going to find out that our approach is very practical to understanding the rates of reaction. And only as we gain some knowledge of the practical aspects of how we deal with reaction rates do we start to introduce theories that help us understand why things are happening the way they are. So these rate laws, the differential and the integrated rate laws for any given reaction are well defined, and each one is determined by the other. And this is all experimental. We're going to get into the theory in a little bit when we talk about mechanisms, individual steps in a reaction. I don't know if I've said this before. Well, let's see, this is the second semester, so you wouldn't have heard me say it in the first semester. But when we put an arrow into a reaction equation, this is overall, right? Usually what happens in here is there are multiple steps in there. And that's where, when we talk about mechanisms, right? These will do certain things, and then something else will happen, and something else will happen before you get to the products. Okay. So we'll go into that in more detail in a little bit. And when we do that, that helps us understand why these experimental results came out the way they did. Okay. I mentioned this just a minute ago. Experimental convenience usually tells us which type of rate law we're going to use to understand anything about the reaction. Which one of these helps us understand it the best. And very often we want to know both of them about any given reaction so that we have that flexibility, whether we want to work in terms of concentration and rate, or whether we want to work in terms of concentration and time. Okay. Right, and I'm hammering this point because it's important. These are experimentally determined, and we're gonna show you how to do that. Okay, so we have this initial rates. We're working with initial rates, and there's a method that goes along with it that's been developed over time to construct to determine the steps in an experiment that will give you the most information, and then will lead you down dead end roads. When I was in research, it was the proper way to do an experiment, any kind of experiment, in the laboratory, in the greenhouse, in the field, was to design the experiment so that you already knew the statistics that would be applied to it before you even start the experiment. That's the ideal. I have encountered several scientists that, well, I call them shotgun researchers. They go out in the field and they grid off their field and they just blast their treatments onto the crops. And then they try to figure out afterwards how to deal with it statistically. They just had that's backwards. You got to know your statistics first, then you throw your experiment together. So I told you that to say that this method of initial rates is one of those procedures that helps channel our efforts so that we get the most information about a reaction and end up with a valid rate law. Okay, that's where I'm going with this. So what we do is we design our experiment based upon how many reactants are in the, if we're going to do initial rates, then we got to know how many reactants, and we really don't care about the products. I mean, we do in terms of, do we know what reaction is going on? Right. We define the reaction in stoichiometry beforehand. But when we go to the initial rates, we're only interested in these concentrations. And at that point, for determining the rate law, we don't care about that part. We don't care about the products. So I just picked 3 reactants. It could be 1 reactant, 2, it doesn't matter. You design your experiment based upon how many reactants you have, so that each experiment, say we have experiment 1, 2, 3, 4, 5. We may not need that many, but I wanted to just throw those up there. So they're different experiments. And what you want to do is choose concentrations, initial concentrations for each one of these, so that comparing any 2 of these will only compare change in concentration, different concentrations, for only 1 reactant. So if I said this one was 1 molar, and this one was 2, and this one was also 2, then I said this one was 2, and this one's 2, and this one's 2. Then when we write the rate law, this is the only one that changed when we compare these 2. So then I would go down to this one and say this one is 2, and this one is 3, and this one is 2. So these 2 would be the same. Then we would be looking at this one, and we could go down and say this one is we could say this one is 1, and this one is 1, and this one is 3, or we could just say 1. Let's do that. 1, 1, and 1. So that's not going to work. Sorry. If we want this one to be the changed one, then we would say like that. Now, which 2 would we want to compare? We compare these 2 here. because that's the only one that changed. Okay, so now that if we only have 3 reactants, we need 4 experiments to give us a comparison that in which only 2 of the concentrations, where these are fixed, this one changes, these are fixed, that one changes, or these are fixed and that one changes. We need 4 separate experiments to do that. So if this is 1, 2, 3, n equals 3, then the number of experiments you need is n plus 1. Okay, so let's look at how we would do that for this particular reaction. If we have 2 reactants, then we would have this differential rate law. Oh, I've already done that one. The overall reaction order is n plus m, and the individual reactant orders is n and n. All right, we don't have to stay on that one too long. And this is just a reality check. How do these exponents, these orders in the rate law, compare to the coefficients in a balanced equation? They don't. There's no relationship. Right? They are unrelated. And the best reason for that I can come up with is the balanced chemical equation expresses stoichiometry. It doesn't say anything about how we get from one side to the other and how fast that happens. It doesn't say anything about reaction mechanisms. Stoichiometry is overall reaction. Now, once we talk about mechanisms and we get individual steps, as it turns out, the coefficients of those individual steps will tell us what the rate law is for each of those steps. All right, so we hold that in reserve. We'll get to that in a few minutes. So, yeah, note at the bottom, the elementary rate law for each one of these elementary steps of the mechanism can be deduced from the individual balanced elementary steps. Okay, so here's how we're going to approach this. These orders, the N and the M and the O and the P, however many you need, these orders, these powers of the concentrations, don't have to be whole numbers. They're just experimentally determined. And what we're going to do is approach it first as if whole numbers are our only option. We're going to introduce 3 types of reactions, and this gives us a bird's eye view of what's happening in terms of rate for the reaction if the order is 0 or if the order is 1 or 2. All right, 0, 1, or 2. Well, fully understanding that when you actually determine those values, they don't have to be whole numbers. Okay, so the first possibility is 0 order. Okay. 0 order. The rate law for 0 order, and this we're going to confine, to simplify things, we're going to confine our discussion to single reactants, like our nitrogen dioxide becomes something. That's the best way to start out, and then we'll introduce more complications later. But we would write the rate law here since it's zero order, it has a rate constant, a rate law constant. Do better. K times whatever the molar concentration of A is to the zero power. Okay? So anything to the zero power is what? 1. That's why this is equal to the rate constant. Now I'm not going to show you the derivation. I may have that somewhere. And it may be a document in Brightspace if you want to look at it. Derive the integrated rate law from the differential. This is the differential rate law. The integrated rate law, where we introduce the variable time, is the differential rate law for this one would be the actual concentration at any given time after the beginning is equal to a minus KT plus the initial, zero, the initial concentration. So we start off at this concentration at any given time T, if we know K, then we can calculate what is the new concentration at that time. That's the value of the differential equation. Okay. So this is what this is how we would graph that information. And notice also the value of this differential equation is, this looks like a straight line. Y equals mx plus b. Okay. And scientists love straight lines, right? They're very well behaved. If we can transform our data in such a way that we can produce a straight line, we're going to do it. So in this case, the slope of that line is right here. It's a negative slope, right? Like that. And its value is K, negative K. That's the slope of that line. And on this graph where we have time on the x-axis, concentration on the y-axis, then that slope is change in A minus change in A over change in time. Okay, so that actually gives us the rate. Change in concentration with change in time, and it's a negative slope. So it's disappearing gradually as we go. And it's equal to the negative value of this K. That's a zero order reaction. And the defining characteristic of this zero order is it's independent of the initial concentration, the rate. It's only proportional to K. Okay, another value that's useful that we can derive from this information, and I'm not sure if I have it on the slide or not, but that's neither here nor there, is the half-life of the reaction. Everybody know what half-life is. I was introduced to half-life in terms of radioactivity. Right? What's the half-life of a radioactive isotope? Well, it's simply how long does it take for half of it to disappear or change into something else, right? And we can use that for chemical half-life as well. So the derivation of the half-life here, E1/2, is simply, we know the initial concentration and we divide it by 2 times the rate constant. That's the half-life. Okay. So the half-life is proportional to the initial concentration. So if we start off with a higher concentration, the half-life is going to be greater for any given a defined reaction. It'll change. If we change reactions, then all bets are off. We got to start all over again. And if we pick our initial concentration at some point in the reaction, right, we can do that. We can say, all right, after the reaction proceeds so long, then instead of taking this one, I'm going to go down here and take this one as my initial concentration and plug it in. And since we've already determined the K, then the half-life, as A disappears, becomes smaller and smaller, then the half-life decreases also. Oh, there's the derivation. Okay, so if we know the differential equation, this is how I derive the half-life. You don't have to know how to do that. I just put that in there for giggles. Okay, that's a zero order equation. First order equation, or rate, first order rate, then would be rate equals rate constant. And these rate constants are not the same. Like we're changing gears here to the first power. Okay. The integrated rate law in this case looks like that one, only in order to get this straight line effect, we have to take the natural log of these values. So we'll take the natural log of A is equal to minus KT plus the natural log of A, 0. Okay. That's the defining difference between these two equations is that one is raw data and this one is the natural log of that data. If it happens to be a first order rather than a zero order. Okay. And this is what it would look like. This is a straight line. And the only way you get a straight line from the data in a first order reaction is to transform it into the natural log value. Okay. Then if you plot the natural log against time, you get a negative slope equal to K. All right. Well, there we go. Now, when we derive the half-life of this one, this is equal to 0.693 divided by A. So notice the difference here is that the half-life for a first order reaction does not depend on the initial concentration of the reactant. It's totally independent. You got the same half-life no matter where you start in the reaction progress. And I should have a derivation for that one too. There you go. If you're so inclined. Okay. So let's take a look at a first order equation with this information as our problem in question. If we have a first order reaction and we know that, and we're given the information that 35% complete at the end of 55 minutes. So let's put that in terms of a graph. Here's our time, and here's our concentration, whatever it happens. All right, so at time 0, we have some value. Okay, some value here, the initial value. And then after 55 minutes, what do we have left? Well, if the reaction is 35% complete, what we have left is 65% of the initial value, right? So I'm going to put that in decimal form. 0.65 of A is left, is the concentration after 55 minutes. So we're told that this is first order. So we're operating with this differential equation. And the ratio of if we work from, let's see, yeah, let's work from this equation. If we work from this equation and we're given the ratio of initial concentration to final concentration is 0.65. So that's why I solved this equation for the A and the A0. That ratio is reference to this value. And the reason I ended up with e to the minus kt value is because if you have log of some, the natural log of some value here equals to, say, y, then what does that mean? Well, the base here is e, right? So this value is equal to e to that power, right? So if I take, this is y, minus kt is y, so e to the minus kt on this side is equal to x, which is our ratio. So that's how the transform worked from natural log to power of e. And the reason I did that is because we're not given the ratio in terms of natural log, we're given in actual untransformed concentrations. So the next thing we want to do is, and we've already done that, is the ratio then is actually equal to 0.65 because it's 35% complete. So that ratio, A to A0, is 0.65. Now we can plug that into our equation, and all we have to do is put a value for t in there. And if we do that, then we have an equation in one unknown, and the unknown is k. Right, so this is what we end up with. 0.65 is equal to e to the minus k times 55 minutes. Okay. Now, how do we get out of this mess? Well, if we have something on this side and we have something on this side, actually, we have e to the y value, right? Best way to get out of that problem is to take the natural log of the equation. So the natural log of x equals the natural log of e to the y, right? And the natural log base e of e to a power is the power. So that's how we got from 0.65 equals e to the minus k 55 down to the next step. Only I introduced, let's see, did I introduce? No. Natural log of 0.65 equals minus k times 55. And now all we have to do is solve for k. So the natural log of 0.65 divided by 55 is 7.8 times 10 to the minus 3. Okay, so that's our k value. We've answered that question. It just took some logarithmic math. Okay, next and last that we're going to study before we start solving problems of a more involved nature is second order. This was zero order, first order, second order. Then would be the rate law would be still some k value a to the second order. Okay. The integrated rate law from that is instead of natural log, now we take the reciprocal of a equals positive k times time plus the reciprocal of the initial. Okay. So we've gone from raw data to natural log, and then we take the raw data and go to reciprocal. And now when we plot it, we get a positive slope, where the slope is equal to k. So what this does is it allows us a tool, a way, a method for determining is the data that we've obtained from a chemical reaction, is it zero order, first order, second order in our reactor? If we have one reactor, all we have to do is say, I've got this raw data here. Say I've got time, right, down this one. Then I've got raw data here. What's that concentration? And it's correlated with this time. If I take the natural log into a separate, and if you know Excel, then it's easy to make that transform. And then I can take that same data and take the reciprocal of it and get another set. If I plot this one, and then I plot these two, and then I plot these two, and this one gives me a straight line, I know it's zero order. But if this one gives me a straight line, I know it's first order. If this one gives me a straight line, I know it's second order. That's the value of doing what we're doing. The biggest value and the most practical way to deal with our data. When we get to the kinetics lab, we're going to use that. Plus one other trick that I haven't talked about yet. Okay. So what's the half-life for this one? Well, the half-life in this case, the derived equation for the half-life in this one is puts the K still in the denominator, but now the initial concentration goes in the denominator. And that sort of makes sense because we took the reciprocal, so it ends up down there. One thing you may also notice is these half-lives, they're all proportional to the reciprocal of K because it's in the denominator, each one. They're all proportional to 1 over K. Okay, and there's the derivation of the second order half-life. All right. So here's another problem, and I've used up my board. See, where am I going to put this one? If we have a single reactant going to products, and we start off, we'll go horizontal then. So I'm going to start off with my data set over here. So we're given initial concentration of 5 molar. So T at 0 time and concentration of, doesn't matter. The initial concentration is 5 molar. Okay. The first 2 half-lives are 25 minutes. So after 25 minutes, this first half-life will be 2.5 molar, right? Half of it's gone. The second half-life is 50 minutes. So this half-life here is 50 minutes. That means we're at 75. But after 50 minutes, another half is gone. Okay? Stop me if I'm losing you. Okay, that's given information. What's the rate law for this reaction? Well, we can already write we can't write the complete rate law yet, but we can preliminary rate equals some K value times the concentration of A to some power. We just don't know what it is yet. What we want to do is determine whether it's a 0 first or second order. And we can do that using half-lives. Let's see. Let's take this information and calculate the K from as if it were 0 order. Okay, so we're going to say if 0 order, then what? If it's 0 order, then the first half-life is 25 minutes. Right? And that's equal to the initial concentration, 5, divided by 2 times K. Okay? So if we solve for K, then K comes over here, 25 goes over there, and we've got 50 divided into 5, which is 1/10, right? So in this case, K would be equal to 0.1. How about the second one? Right? Now, remember that the half-life doesn't change for a given reaction. So we should get, if we do the half-life for this one here, it should give us 0.1 if it's zero order. Okay, so now the initial concentration is going to be 2.5 for our half-life calculation, and the change in time is 50 minutes. So the half-life is 50 minutes, and that's 2.5 over 2K. So 2.5 divided by 100, correct? I don't think we're going to get the number we're expecting. 2 times 100, bring the K over here, 2.5 divided by 100. No, 0.025. So K equals 0.025. So zero order, it ain't it. All right. What if we do first order? Well, let's look at first order. First order is dependent upon the half-life for a first order is not dependent on initial concentration, right? So do we have different half-lives here? Right? We're going from 5, 0, 25 minutes. We get a half-life of, half of it is after 25 minutes is 2.5. So is this dependent upon concentration? The initial concentration here gives us, it's changed from 5 to 2.5, initial concentration, and the half-life changed from 25 to 50. So it's not first order, because first order half-life is not dependent upon concentration. So we can throw that one out. And let's go confirm if it's second order. Right? So we're talking about 1 over K times initial. So let's do the first half-life for this one would be 1 over K times initial concentration is 5. Well, put a value in here. First half-life is 25 minutes. Okay. So K then is 25 times 5 reciprocal. 25, 5, and take the reciprocal. It's right here, 0.008. So K in this case, 0.008. Then we do the second one, which is 50 minutes, 1 over K. And its initial is 2.5. 2.5. So K in this case, bring K over here, put 50 over there, is 2.5 times 50, and take the reciprocal, 0.008. That's the one. This is a second order equation, and the value of K is 0.008. Excuse me. Okay. So there was our first calculation, 0.1 and 0.025. And then the second one, we already did away with the first order because it's not dependent on, the half-life is not dependent on concentration, initial concentration. So then we went on to the second order and did that calculation. And that's where we got 8 times 10 to the minus 3 or 1008. Okay, now that we know that, there was another question, wasn't there? What is A at t equals 525 minutes? So now if t, we know it's second order, okay? So we can use the second order differential equation right here. You can use that. So we want to know what's this value right here. That's unknown. But we know this value, 0.008 is K. And after how many minutes? 525 minutes. So if we're going to use 525, we have to start with 5 molar. So this is 1 over 5 molar. And then we solve for A. I'm going to save a little time and just go to the next slide. Okay. There we go. 1 over A is 4.4, and A then would be the reciprocal of that, 0.3. 0.32. 23. Dyslexia is kicking in. There we go. All right, so there it is all on one page. The rate law then would be, I guess I didn't put it up there. Would be K times A to the second power, and then we insert K. Would be 0.008 times A to the second power. That would be the rate law. Okay, I already told you this one, but here it is in black and white. How do you tell the difference between 0, first, and second order? Oh, that next slide. All right. Oh, no, this is different. What if we have 2 reactants? We've only talked about order for a single reactant equation. If you have 2 reactants, what we do is we increase the concentration of one of those reactants to the point that its concentration barely changes during the reaction. It's just minuscule change. So if we start off with rate equals rate constant, then we have this reactant to its order and this reactant to its order. And let's say we increase this one right here so high that it doesn't change during the reaction, right? So it's essentially constant. So we've got a new constant now, say K prime. It's going to be K times this value. Okay. Now our rate law becomes this. The true K, no, K prime, sorry. K prime times that term. Now we can conduct our experiment. As long as we keep this one high, we can conduct our experiment and find out whether this was 0, first, or second order. Yeah, there we go. Now I'm gonna expand on this idea when we get to the kinetics lab experiment. But that's the way we handle it. It takes a little more math at the end to tease out the order for the the B reactant. Okay, so here it is all in one place. Everything we've talked about so far. And point of this slide is to focus your attention on what we, as a practical matter, what does the order mean? 0, first or second order. Well, if we take a reaction where we're saying A yields to products, we start off with 5 molar again, and we know that the K is 1 times 10 to the minus 2, but we're not saying what the order is. We're saying it's either 0, 1, or 2. And we're going to do a calculation with our differential rate equation for each one of those and say, well, if the reaction is 0 order, and we put in this information into the differential equation, what is the final concentration? Then we do the same thing with this equation and the same thing with this equation and see what is the difference? What can we expect as the outcome after the same amount of time, 30 seconds have passed? What can we expect from the final concentrations of our reactant? Right? What do you think? Just in general, is it going to stay the same? Is the final concentration of A going to be the same for each one of them? Is it going to be higher or is it going to be lower?
It'll be different for each of them.
It'll be different. Okay, I got that one. Do you think it's going up or down? We're talking about the disappearance of the reactant.
It's down.
Yeah. Yeah. So the second order should be the lowest concentration after the same amount of time. And this is the set of calculations that tell us, okay, if it's 0 order, we're going to end up with 4.7. It's almost the same amount. If we do a first order calculation, then a little bit less, 3.7 molar. And if we do a second order calculation, we're only going to have 2 molar left over after 30 seconds. Okay. So that sort of gives you an idea, an intuition of what order means. If we increase the order, the reaction rate's going to be clipping along faster. Okay, here's our method of initial rates. Yeah, I guess it's going to get too busy if I leave all this stuff up here. So we're going to do initial rates experiment based upon this equation. And the way I set it up, if it's initial rates, then we're interested in the balanced equation, but only the reactant side. So when I set my data up to run this experiment, I'll put manganate ion here. I'll put it looks like oxalate, oxalic acid, C12 here, and hydrogen ions here. Okay. So those are going to be concentrations for our various reactions. So how many should we have? Separate experiments. We should have 4, right? Because we have 3 reactants. One thing you'll notice is charges don't balance. The reason for that is we've left out the spectators. Okay, so here's our data set. And we have, I'm going to refer to that. It's set up this way, right here. Oh, and these are initial concentrations for each one. And each one of those rows represents a separate experiment. And then we have the initial rates. Let's see, in molarity per second. Those values are over here. Okay. So first thing I do after I set this up, and I would write in my values, of course, is I write the rate equation with the orders, substitute variables for the order. So the rate equation then would be equal to some K value times the initial concentration of the manganate ion to the N power times the oxalic acid concentration to the M power times the hydrogen ions to the N. I'm not going to write O because that implies zero order. I'm going to write P. Okay, so that's what we're working with when we say the rate. We're given rates for the reaction, initial rates, that is at the very beginning of the reaction. This is the rate, each one of those values. Okay, so if we want to find out what this one is, these two need to be constant. And first and second one would be a good choice. Right? So here's what you do. If we're working on this one first, then we set up this rate equation. So the first set of data would be rate. What's the rate for the first? 2 times 10 to the minus 4, right? 2 times 10 to the minus 4. And I'm going to leave the units out just because of space. And then that would be equal to some K times the value for this one, which is 1 times 10 to the minus 3 to the N power. And then the next one would be 1 times 10 to the minus 3 to the M power. And the last one would be 1 to the P power. Okay. Then the second one is 8 times 10 to the minus 4. That's not going to work. This is the first one, right? I'm going to put the second one up here. And I'll show you why I'm doing that. Wait a minute. Yeah, that's right. The second one, this is the rate for the second one. 8 times 10 to the minus 4. 8 times 10 to the minus 4 then is equal to K. And this value then does change to 2 times 10 to the minus 3, correct? To the N power. But these are stay the same. To the M, and this one to the P, correct? Put those in there, right? Okay. So here's what you do. You ratio equations. Okay. The reason I put this one up here is so that it would give me a whole number, not a fraction. So what's 2 into 8 is 4. Okay. K divided by K goes out. These terms go out. That. And we have this one divided into this one, which is when we say A to the N divided by B to the N is the same as A divided by B to the N power. So we say 2 divided by 1 is 2 to the N power, right? So what would N have to be to give me 4? N is 2. Okay. So this one now is second order. Okay. We do that for each one. We pick the experiments so that they cancel 2 terms out of the expression and leave only 1 ratio behind. So if we're going after this one, it changes. Let's see. The second and the third one would be a good choice for that one. right? Because manganese, the manganate ion and the protons are the same concentration, but the oxalic acid changes. So I'll put the bigger one on top just because it's easier to do. 1.6 times 10 to the minus 3. And then the one above it is 8 times 10 to the minus 4. That's equal to, and we're going to have K's and K's cancel. We're going to have the manganates cancel, right, because they're the same. And we're going to have the hydrogens cancel, right? Right, cancel. All we have left then is 2 divided by 1, right? 2 times 10 to the minus 3 divided by 1 times 10 to the minus 3. And this is to the n power. Okay. So what's all right, this is these, if we're going to do this in our head, these have to be the same. So which way do we want to go? I'd make this one smaller and move that decimal to the right. Right. Make this one 10 to the minus 4. And that means this one is 16. 16 divided by 8 is 2. And this one is 1 into 2, which would be 2 to the n power. So n would be 1. Right? So we can erase this m, and it's understood to be 1. Okay? Now, let's see. Save myself some writing here. Now we want the 2 that give us the hydrogen ions. Okay? So that will change these values. Which one where the hydrogen changes? The last 2. So the last one and the one before it. So I would put 1.6 divided by 1.6. 3. And 1.6. These are the same, these are the same, these are the same. And these go from 2 here to 1 there. So this is 1 equals 2 to the p power. So what would p have to be to give you 1? 0. Okay. So p is the 0 power. All right. So when we know what these values are here, we haven't got the k yet. Excuse me. Well, that's jumping too far ahead. We know what these values are, 2, 1, and 0. But when we write the equation out, this term disappears because it's 0 order. Right? Even though it's part of the equation, it doesn't matter. It's 0 order. Nothing changes. So we would write it this way. Rate equals K MnO4 minus and H2C2O4 to the first power. That's it. That's our rate equation. We just don't know what K is yet. So how do we find K? What we do is we take one of those experiments, pick any one you want. And we plug the rate in here, the values here, and solve for K. So I just take the first one. So 2 times 10 to the minus 4 equals K. And then the manganate, and that would be 1 times 10 to the minus 3 squared. And then 1 times 10 to the minus 3 here. And that was 1. But it's not a term. So we go ahead with this one. Well, if that one's squared and this one's first power, we just cube this one. Right? So what's 1 times 10 to the minus 3 cubed? 1 times 10 to the minus 9, isn't it? Yeah. So this is K times 1 times 10 to the minus 9 is equal to 2 times 10 to the minus 4. And then K is equal to 2 times 10 to the minus 4 divided by 1 times 10 to the minus 9. Right? Yeah. Okay. So this is 2. And the exponents, this one comes up here as a positive 9, minus 4 is a 5. So that's our K value. And if we write the equation out, knowing what we know now, we would say the rate law is this. Rate equals, what's the K? 2 times 10 to the 5 times MnO4 minus to the second power and H2C2O4 to the first power. That's our rate law. Okay. And then since we didn't write the protons in there, you would know based upon the balanced equation that it is a reactant, but it's only it's the 0 order because it's not there. Okay, does that look difficult? Time consuming. Yeah, it's like a labyrinth. It's easy to get lost. So you have to be very methodical about your approach. Use lots of scratch paper. Okay, now we're going to talk about mechanisms. Up to this point, we've used experimental evidence to determine the overall rate law for a sample reaction. Now we want to break down reactions in terms of their mechanisms, right? What are these individual steps? And the overall rate law and the balanced equation help us propose different mechanisms. I smell eggs cooking. Or is it just me? Smells like greasy eggs. Most chemical reactions occur as a series of elementary steps. So in this process, what usually happens is the reaction produces some products, and very often one of those products is an intermediate. An intermediate is the product of an elementary step that appears inside the reaction, inside this arrow. An intermediate appears inside that arrow. But disappears before we get to the end. It occurs in here, but it's gone before we see it. Okay. Here's an example. NO2 plus carbon monoxide. This is a proposed two elementary steps in this reaction. And the first step is where we have, we have two NO2s reacting with each other. So instead of writing it like those space filling models, I'll say the first step, step 1, is two NO2s yield what? They yield an NO3. NO3 plus an NO. Okay? Notice that the products contain NO and CO2, right? We know the overall reaction. So there's a product that's in the overall reaction. There's an intermediate. So we take that intermediate for the second step. The intermediate and react it with carbon monoxide. And what we get then is an NO2 plus a carbon dioxide. Okay. So let me put the overall reaction up here. NO2 plus CO yields, and these are all gases. I'm going to write that in. NO plus CO2. That's the overall reaction. These are the steps that are proposed. Notice that we started off, this step has two NO2s. So in the reaction mixture, you don't have just one NO2 floating around. You have billions of those things. So it's reasonable. I mean, we could react two of them. But we react two of them in this step, but we produce one as a product over here. So what happens when we add them together to produce? If you have a proposed, and this is like brainstorming or spitballing, you just create any mechanisms you can think of. And then you eliminate the ones that are completely off the wall. And then you go for the ones that are less likely. And finally, you narrow it down to maybe, hopefully one, but maybe two. And then you have to tie break and say which one satisfies the data the best. But in this case, if we say that two NO2s here, but we produce one on that side, then one of those NO2s cancels out here, and that just leaves us with one NO2. Right? The NO3 over here cancels the NO3 on this side. So it's an intermediate. It's gone. So we bring this one down as a reactant. That one's gone. This one's gone because we used up one of those. And then we have NO plus CO2 left over. And when we add these elementary steps together, we get the overall equation. That's the first condition for a proposed mechanism. You have to be able to add them together and end up with the overall reaction. If you can't do that, then you throw that mechanism out. Okay. This concept called molecularity. That sounds like a funny word to me. Anyway, molecularity refers to how many molecules are involved in the elementary step. In this case, we've got two. I mean, they're the same molecule, but there are two of them that have to come together in order to produce that. So it's bimolecular, collision of two species, right? And in terms of order, the molecularity tells us the order of this step. So if two of them come together, this is second order for that elementary step. If only one of them would react, it would be unimolecular. And if three of them come together, that's termolecular. Unimolecular is fairly common. And if you only have one, not two, but one on this side, then it would be unimolecular, elementary step, and have a molecularity of 2 or 1 plus the order for that one would be 1. But if we had 3 of them come together, it would be termolecular. The thing about these molecularity ideas is that it's fairly easy for unimolecular to undergo a reaction because it's only dependent on itself and the amount of energy that's supplied to make the reaction go. Bimolecular is not much more difficult than unimolecular. You only have to have 2 molecules approaching. They collide with the sufficient energy and with the proper orientation so that the reaction sites on the molecules have a chance to interact and produce products. So the bimolecular is not that rare either. Termolecular is almost never happens
because it's very difficult to get three molecules coming at each other, colliding with the amount of energy they need and the proper orientation for all three of them to start the reaction, to make the reaction go. So termolecular is an elementary step that we rarely use in a mechanism. Now, it's not unheard of, but you go to termolecular when you have no other options. Very rare. And it would be considered a third order. Like third order, we haven't talked about third order. But I guess you could say the sky is the limit. All right. So one of the and this one is also second order because it has two. One of the useful derivations of reaction mechanisms is an understanding of the reaction rate in terms of an elementary step, because these are rarely occurring at the same rate. This one occurs at its rate, right? And this one occurs at its rate. Now, think of it as a bottleneck, right? If you're trying to push fluid through a pipe and it narrows down here, that's your bottleneck. And that determines the rate of the flow, or the rate of the reaction. So the slowest step determines the overall rate. And that's our starting point. Once you've got a mechanism that you think is correct, then you use that as your starting point, equal to the rate that you determined experimentally. And you work from there. Okay. Okay, these are requirements. I covered one already. When you add up the elementary steps, they must equal the overall balanced equation. That's the first condition. And the mechanism must produce results equal to the experimentally determined rate law. So when we combine these into a rate law, which we can do, because we know that these coefficients lead us to, and the number of reactants lead us to the molecularity and the order for each of those reactants. Then we can construct a rate law from the elementary steps. And if that rate law, the theoretical rate law, agrees with the experimental rate law, then that's another confirmation that this mechanism is valid. Okay, here's another example. We have dinitrogen pentoxide reacts to produce nitrogen dioxide and oxygen. And this is the proposed mechanism. Step 1, 2. This is a 3-step mechanism here. What we're saying is one of those dinitrogen pentoxide molecules decomposes into NO2 and NO3. So NO2 is a product from the overall reaction. NO3 is an intermediate. And we're proposing this reaction as very fast. In fact, it's not just fast, it's so fast that it produces products so fast that the return reaction sets it into an equilibrium situation. It's what's called a fast equilibrium. The slow step, we take the NO2 from the product of the step 1 and react it again with the NO3 to produce now NO2 and NO2. Right, so now we've produced an NO2 from in the second step, and we've produced an oxygen, and we've produced another intermediate. So in the second step, we consumed NO3 intermediate, we produced another intermediate, NO. And then in the in step 3, we're proposing an intermediate NO3 and an intermediate NO produces 2 NO2s. So first thing we have to do, we know that the rate is going to be governed by step 2. But we have to add those up and be sure that they're consistent with the overall balanced equation. Right? And in order to do that, we've got to use Hess's law. Right? We might have to multiply a whole number times the first one, right? Because we only have one N2O5 available in those steps. We need 2 of them. So we're going to say 2 times that. And that way, one of those NO3s cancel from step 3 and step 2 also. And since we multiply by 2, we have 2 NO3s that cancel both of them. It's 2 NO3s on this side, 2 on this side, they cancel. Those intermediates are gone. Then we're going to cancel the NOs. Well, we can cancel the NO2s on either side also. And the NOs we can cancel because they're on opposite sides of the arrows. So what's left over? Well, left over is 2 N2O5s, 2 NO2s from the first step and 2 NO2s from the third step. That's 4 NO2s, we're good. And 1 oxygen from step 2. So overall, we have that validation of our steps. All right. So that's as far as we're going with that one. We're going to take this example where we have imaginary reactants and products. A plus 2B yields C. So we propose this mechanism, A plus B yields D, and D plus B yields C. Now, if we add those together, the D's cancel. We have 1A, 2 B's, and a C. So as far as that goes, it's valid. So how do we approach the rate law? Let's see, did I do it step by step here? Yeah, it met the first condition. Yep. So if we're going to write a rate law for each of these reactions, we know that the fast step is A plus B equals D, that intermediate. And a fast equilibrium means that the forward rate is equal to the reverse rate at equilibrium. Now you're getting a little bit of chapter 13 in here. Now the slow step is so slow that it dominates. I mean, it determines the overall rate. So that's where we want to start. This K2 is the rate constant for that separate step. So we would write the rate law in terms of the slow step first. So we'd write the rate equals that K2 times the concentration of D times the concentration of B, and each one of those is first order because there's a 1 coefficient in front of each one. Okay, so that's how we get the elementary step rate law from that one. We can't keep that as the final rate law because there's no D in our overall reactants. So we have to find some substitute for that D. So here's how we do that. Right, D is not a reactant, it's an intermediate. So we're going to take the fast equilibrium and we're going to write an expression for the fast equilibrium. Right? The forward rate equals the reverse rate. So the forward, I skipped a step. So the forward rate law for the first one would be, let's say, rate for K1 equals K1 times A to the first power times B to the first power. Okay. And the rate for the reverse, say K prime 1 equals the reverse. So it only has D in it. So this is a K prime times D. Those rates are equal. So that's why we set them equal to each other in that expression. And then we just solve for D. D equals K1 over K prime times A times B. Then we can substitute that term on the right into our previous equation. And here it is, substituting. So this is where we get the overall. We've gotten rid of D because we substituted what that expression is equal to, and then we condense it. The K2 times the K1 divided by the K prime is a constant. Right? It's still a constant. We got products and quotients of constants. Put them together, you get one constant. And that's our K value. Then we combine the rest of them. A is still first power, B then is second power. So the overall rate law is rate equals K times A times B to the second power. Okay, that's how we derived an overall. And what we would have to do is we would have to experimentally determine the rate law for that reaction and compare it to this derived one and see if they agree. How close do they agree? Because the experimentally determined one might have some error built in. Okay, now I've already introduced some of this to you already. This is the collision model. And at its most basic understanding, the collision model just says, if you don't have a collision, you don't have a reaction. So molecules must collide in order to have a reaction. And some other conditions must be there, must be available so that the reaction can proceed. The first is called activation energy. E sub A. Activation energy must be sufficient. It has to be a minimum value for the reaction to proceed. And that's not always, but usually related to temperature. But it can also be light. Let's see. H nu, that's equal to H. Some reactions you can set them off with a photon of light if it's high enough energy. That usually means ultraviolet. And then that condition must also be paired with orientation. The molecules, when they collide, they have to, if their reaction sites for this reaction are on opposite sides and they collide, nothing happens, they just bounce off. So if their reaction sites are on the proper side and they impact one another, then you have the opportunity to break bonds and form new ones. So orientation and activation energy are absolutely essential during a collision for a reaction to proceed. Those are the essentials of the collision model. Okay, back to our old energy diagram. If we have a total energy on this axis, and that's the total energy of everybody, reactants and products. And if we say start off, let's see, they started off there. I'm going to start off here. Reactants. Now we're talking about this can be overall or it can be elementary steps. Either way. And we're going to, as the reaction proceeds, as the collision proceeds, progress, we're talking about an elementary step. As the collision proceeds, you build energy in those reacting molecules, and then reach this activation energy, this hump. And if it's enough, then they start to form a transition state or an activated complex. It goes by both names. Transition state or an activated complex. And what we've represented there is dashed lines. So if we started off with BRNO, then what we're doing is it looks like we're retaining the bond between BR. Let's see. No, we have BRNO, right? BRNO, just a simplified version. And what we're doing here is these two are coming together. And what we're doing is we're breaking these bonds and we're forming that bond. So the NOs go away as two separate molecules. And the activated complex then starts to form the BR, the dibromine bond, and break this one. That's why they're dashed. One of them is being broken. These two are being broken. This one's being formed at this energy level. And if we have that minimum amount, then we go over the other side. Well, in theirs, the products are at lower energy. So I better stick to that since I'm talking about it over here. So these products are at lower energy than the reactants, which means what? Where does that energy go? Usually heat. That excess energy that was contained inside the reactants now is outside the reactants, and we have products with some heat. This is an exothermic reaction. So the activation energy is between these two. Right there. In this direction. And the this one is delta H, the enthalpy of the reaction. Okay. So this reaction could go backwards. Right? If we went backwards, what would the activation energy be for the reverse reaction? For the reverse reaction would be greater than the forward reaction. Okay. And this just restates the concepts behind the collision model. Now, what impact does this have on the reaction rate? Well, first of all, we need a way to calculate the activation energy or use the activation energy to tell us something about the reaction rate. This is the Arrhenius equation in its purest form. It's not very useful that way, except to say what is the relationship among these values. That little k over there is the reaction rate constant. A is some proportionality constant. Let's see. E is the base of the natural log. And then capital E sub A is the activation energy. R is the gas constant with the energy term in it. So it's 8.3145. And the temperature is in Kelvin. But like I said, that's not very useful. What we need is a useful form of that equation. And here's the linear form of the Arrhenius equation. If we perform 2 or more experiments, and we determine, or we could do 1 experiment and determine the K value, actually several experiments. Let's say at different temperatures. So we have different temperatures, and we determine the rate constant, which will change with temperature, right? And we get this data set. Then we transform this one. We take these temperatures and do a transform 1 over T, get that data set. And we take the natural log of this K, right? And we plot those two. This on the y-axis and this on the x-axis. Then we get a graph with natural log of K and 1 over T here. And we get a negative slope. Like that. And the slope of that line is equal to minus E sub A over R. So that way, if we determine what the slope is and set it equal to that, we can calculate the activation energy. And then wherever it intersects up here, right, this is the natural log of A, which is neither here nor there, actually. Okay, so there's our example for a given reaction. Let's see, how much time do I have? 12:30, and the lab is supposed to be over at 1:30. Okay, how many more slides do I have? Any further wait time? Okay. Rather than work this one out on the board, I think it's worked out in the slide set. So we'll just talk about it. But it's a puzzling question. I've always learned, my first degree was in biology. And one of the rules of thumbs that we always talked about was reaction rates. And how fast would a reaction rate, whether it's inorganic or organic, doesn't matter, biochemical reaction, what would be the effect of reducing the temperature? Well, overall, we say reduce the temperature and the reaction rates slow down. Okay. So, and the rule of thumb was for every 10 degrees Celsius that we reduce the temperature, we cut the reaction rate in half. Or if you want to heat it up, if you increase by 10 degrees, you double the reaction rate. Okay. So I was curious when I was working these slides. This is not one that came from the publisher. I put this one in here myself. I was wondering if we went from 25 degrees to 35 degrees, what would be the activation energy for a bona fide biochemical reaction that would give us a doubling of the rate? So we're increasing the temperature by 10 K. What would have to be the activation energy for that rule of thumb to be exactly double reaction rate? So that's where I've gone with these calculations. That one on the left is converting 25 degrees to K, and the one on the right is the final temperature, 308 K. Right? If we use Arrhenius' original equation, and we set the K1 equal to that expression and put the T in and put the R in, and our unknown is E sub A. And we do the same thing for the increased temperature. Well, the new K would have to be double what the original K was in order to double the rate. So that's why I set it equal to K2 times K1. And then if we ratio the K2 to K1, which would also be 2K1 over K1, then that's going to be 2 because the K1s cancel. So that's doubling of the rate. And that's equal to the ratio of those two Arrhenius equations. Well, through a little sleight of hand, mathematical sleight of hand, we end up with that bottom equation where 2 is equal to E to that power. And it includes both temperatures before and after, plus the activation energy. Next, I took that equation and let's see, what did I do to it? Oh, I took the natural log of that equation. Okay. The natural log of the right-hand side is simply the power of E. And the natural log on the left-hand side, of course, would be natural log of 2 times R. And the R was in the denominator, I believe. Yeah, R was in the denominator, and I already brought it across. So I kind of combined 2 or 3 steps there. So now we want to solve for E sub A. And that's what I've done in that middle formula. And then in the bottom, I plug in the actual values, right, for the temperatures. And when I do that, the activation energy that would exactly give me a doubling of rate for a transition from 25 degrees to 35 degrees is 52.9 kilojoules. That's the activation energy that would give me that value. If the activation energy is less than that, we get less than doubling. And if it was greater than that, we get greater than doubling. Okay. This should go pretty quick. What is a catalyst? I like to look at it this way. If we have A plus B yields, let's see, we have step 1. Oh, for our overall reaction is A plus, it was 2B, wasn't it? 2B equals C. If our first step is this one and it produces D, this is an intermediate. Because it's going to react with something else over here and be gone. Okay, that's an intermediate. However, if we have an equation where we have, let's say, A plus 2B plus D yields C plus D. D goes in this side and it comes out that side apparently unchanged. And this is the overall. This is the overall, not an elementary step. Now, if it was an elementary step, D would come in on this side over here and go out on that side, rather than being produced over here and disappear from this side. That's an intermediate. But a catalyst comes in as a reactant on the reactant side and goes out on the product side, apparently unchanged. Okay, that's the difference between intermediate and catalyst. Now, the other part of the definition is that what good is a catalyst if it doesn't change the reaction? So the catalyst does actually participate in the reaction. It just doesn't look like it overall. But what a catalyst does is it causes the reaction rate to increase. So we would have a separate rate equation for a catalyzed equation, and we would have separate intermediate, separate elementary steps involving the catalyst. So it's a completely different pathway when a catalyst is involved. And what the catalyst does, it reduces the activation energy. The size of the activation energy is decreased. So if we drew that in our energy diagram, right, progress this way, and say we went like this, let's see, went up like that, down like that, then our uncatalyzed activation energy would be here. Our catalyzed be like that. And this is catalyzed activation energy. Well, there it is. We start at the same place, we end at the same place, but because this is lower, we get there quicker. This is another way to look at it. Why is the catalyzed reaction quicker? If the activation energy is less, then on this diagram, we see the distribution of energies in that curve. So the number of collisions that produce reaction for an uncatalyzed, they have to have a certain minimum energy out there to the right in that blue section. If we introduce a catalyst, then we include lower energies. And that gives us more collisions that actually produce reactions. Looks like a chi-square curve. Did you get that in biology? That was my first introduction. We had chi-square statistical test. It's okay. Or actually, the chi-square was one of them, and the student's t-test was another one. Yeah. Okay, anyway, we can characterize catalysts in terms of their relationship to the reactants. So if the reactants are in one phase and the catalyst is in a different phase, we say it's a heterogeneous catalyst. They're in two separate phases. The best example I can think of is gases from your internal combustion engine going out your tailpipe, and they hit the catalytic converter. The catalytic converter is filled with solids. And gases against a catalyst that's a solid, that's a heterogeneous catalyst. And in order for this catalyst to work, a process called adsorption has to occur. Absorption is like you stick a paper towel, or you lay a paper towel on a wet spot in your countertop, and it absorbs the moisture. Adsorption is a surface phenomenon where molecules come and they sort of attach themselves to the surface of the material. So how does this type of catalyst work? Well, first you have to adsorb the reactants on the surface of the catalyst. Right? This is called a process of activation. Then they tend to migrate along that surface toward each other. And what the catalyst does is it as they attach themselves to the surface and they come closer together, they are properly oriented for the reaction to occur. So that's part of the process of speeding up the reaction. And then once the reaction occurs, they desorb and go on their merry way. This is what a catalytic converter looks like now. It's got a ceramic honeycomb in that can, and coated on the ceramic base are the catalysts, usually platinum and palladium. And it doesn't take much. Maybe a couple of atoms thick on that surface. The original catalytic converters had little beads. These little ceramic beads, and the beads were coated with platinum and palladium. So enterprising shade tree mechanics said, these catalytic converters are robbing my engine of horsepower, which they do. So I'll just go under there and I'll take my screwdriver and go, bam, knock a hole in it, right? And out come the beads. And then I'll just kind of braze it over and polish it a little bit so it won't be noticed. And I can go on my merry way. That was before they tested your exhaust. Some cities, yeah, like Los Angeles, Atlanta, I think does, they have pollution inspections of your vehicles. So some enterprising engineer decided, okay, we're going to fix that. We're just going to turn that ceramic matrix into a solid, right? A honeycomb solid, and dare you to remove it now. So it takes these partially reacted gases. NOx is oxides of nitrogen. HC are uncombusted carbohydrates. No, not carbohydrates. Hydrocarbons. And then CO is partially oxidized carbon. and it turns them into carbon dioxide, water, and nitrogen, which are already in the atmosphere anyway. Okay, homogeneous catalyst is one which is in the same phase as the reactants. One example of that is enzymes in each one of your cells. They're all in this aqueous matrix, and the enzyme acts like a catalyst. I'll hold on to that thought. Other types of catalysts, that's an organic catalyst, an enzyme. And most enzymes are proteins. There are a few that are RNA molecules. But another example of an inorganic catalyst is aqueous iodide ions, usually as potassium iodide. And if you add that together with hydrogen peroxide, this reaction goes really, really fast, right? It leaves the iodine unchanged, and you end up with water and oxygen gas. Which means I need, let's see, two here and two there. That's balanced. So I had a student in a class I was teaching at Logan for the Southern, and he and his, I don't know if he was married to this woman or not. Anyway, they were expecting a child, and they had the ultrasounds. They were going to have a reveal party. So he got a 2-liter bottle, and he put 30% hydrogen peroxide, which you have to order special, in there. And he added a little soap and a food coloring, right? You know, red for a boy, blue for a boy and red for a girl, because it'd come out pink. And they put the color in there. He put the color in there, and then to reveal, you couldn't see what it was going to be. To reveal, he poured the solution of potassium iodide in there, and it went everywhere. I forget what color it was. It was the wrong color. They had another ultrasound and found, oops, wrong gender. So they did another party. And that was his gender reveal. And that's a homogeneous catalyst. It's in the same phase. This is not a gas. This is a liquid. It's in the same phase. This is a gas, and this is still a liquid. That's a homogeneous catalyst. Okay, back to enzymes. There's a major difference between inorganic catalysts and organic catalysts. Inorganic catalysts catalyze both directions. And the only way you can control that is with concentration and temperature. But it's not really control. Enzymes, on the other hand, usually catalyze in one direction only. So we have an enzyme here, one going that direction from reactants to products. If you want to go back the other direction, you need a different catalyst, a different enzyme to do it. That's how our body, or how any biochemical system, controls the production of product and maybe the return to reactant. The other thing is, these enzymes, many of them are what we call inducible. And otherwise, they might be in your cell, but they're dormant until they're activated. Or even, they might not even be there until the substrate, this is called the substrate, until the substrate appears, and the substrate induces your DNA to be transcribed into RNA and produce the protein for the reaction. So, and in addition to that, control feature is temperature dependence. Inorganic catalysts operate over a wide range of temperatures, and some of them operate at very, very high temperatures and pressures. But enzymes, if you get the temperature too high, let's do it the other way. You get it too low, then it doesn't function. It just sits there. If you get it too high, it may be denatured. You can denature a protein, right? We do it all the time when we make cheese. We coagulate the proteins and make cheese. But if you do it to the enzymes in your body, too high temperature, like you're running a fever, then your first thing is the enzyme doesn't function properly at high temperature. And then if you get high enough, they start to denature, and that can be fatal. So I see that as the difference between our body temperature at 98.6 degrees and the body temperature, the normal body temperature of a cat or a dog, around 100 degrees. They even go higher than that when you take them to the vet. They get really nervous, temperature shoots up. So those major difference between organic enzymes and inorganic catalysts. Okay, I got a video. Oh, it's not going to go. Here.
You can try yours. So that's the technique. Just dump it right in and see what happens.
Oh wow. Okay.
Okay. So
Whoa.
we're releasing
Okay.
lots and lots of oxygen gas. Okay. So why don't you go ahead and do yours now? Yours is a little bit different container. It's got, just dump it in really quick.
Okay.
Perfect. Yours is like more. And you just generate tons and tons of oxygen. It's being trapped by the soap, okay? It's like a supersized version of what kind of happens when you pour it on your body.
Sure.
Where that catalase enzyme breaks it down.
But again, we're not actually cleaning anything, if you will.
Technically, the hydrogen peroxide, when it generates this oxygen, can kind of dislodge big hunks of stuff. This is like more of
Okay. Let's see. He said something I was going to comment about. In your body, one of the damaging products, the byproducts of some reactions, are called peroxides. They're very reactive, and they can damage parts of your cell. They can even damage DNA. So we have inside our cells built in, always there, peroxidases. Peroxidase. Anytime you see the name of a compound with ACE on the end, it's an enzyme. And what the peroxidase does is it causes this peroxide linkage of any kind. Right? This is hydrogen peroxide, so that would be hydrogen, that would be hydrogen. But peroxides can form with any molecules, and these are very reactive. So what the peroxidase does is it breaks these bonds and rids your body of those things. And they think there's one theory that says that's why your hair turns white, because the peroxidase activity goes down as you age, and it leaves those peroxides in your hair follicles, and it bleaches your hair when it comes out. I don't know if that's true, but that's one theory. Okay. There are various catalyzed reactions that are good and various catalyzed reactions that are not good. This is the proposed mechanism for hydrogen peroxide. It's a 4-step reaction, and the first step is the slow step. So it can get really complicated. And this has been confirmed. So our rate law would be based upon that first step. And notice that iodine goes in the first step, and it produces some intermediates, and it comes out in the last step. So, supposedly unchanged. Okay, bad types of catalysts. We have in our upper atmosphere a compound called, actually it's an allotrope of oxygen called ozone. It's extremely good at absorbing ultraviolet light. Okay, so if we decrease the amount of ozone in the upper atmosphere, then that lets more ultraviolet light filter through. and that can cause damage to living systems. In this case, one of the catalysts is nitrogen monoxide, nitrous oxide, laughing gas. No, that's not laughing gas. That's nitrogen monoxide. N2O is laughing gas. NO then is a catalyst. It's produced as a byproduct of internal combustion, mostly. And it drifts slowly to the upper atmosphere and causes this damage. And the ozone is produced by these ultraviolet rays. So we get oxygen. I don't remember the exact reaction, but it impinges on oxygen molecules and they combine to produce ozone. And this ozone is much, much more effective, right? So the more ozone you have in the upper atmosphere, the better. Now, we don't want ozone down here because it's extremely reactive. When laser printers were first introduced, one of the byproducts of the laser reaction, the laser printing process, was the production of ozone on the inside of that machine. So initially, their stopgap solution was to put these activated carbon packets in there inside the machine close to where it was being produced, and they just absorb it. But with advances in technology, now they produce laser printers with very low ozone output. But ozone can damage your cells. And in fact, there are some municipalities that use ozone as a treatment for sewage and water treatment for drinking water. They bubble ozone through it and it kills everything. I think Atlanta uses that. I used to live in Atlanta, so I think in those terms. Okay, so ozone depletion is a bad thing. And other molecules that can drift to the upper atmosphere and also catalyze these bad reactions are the chlorofluorocarbons, freons, right? Initially, this dichloro-difluoro freon 1,2, freon 12, was notorious. And in the upper atmosphere, light would impinge on it and split off a chlorine atom. Like that. Individual chlorine atoms. These are known as, this is one type of free radical. A free radical has an unpaired electron, which makes it extremely reactive. And it would destroy the ozone. This is how it does it in this two-step reaction. It destroys the ozone. And the thing about catalysts is, once you get a catalyst in a reaction environment, it can catalyze that reaction and then go catalyze another reaction. So a little bit goes a long way. And it's taken decades to reduce the amount of these freons and nitrogen oxides in the upper atmosphere, of controlling our use of these things down here to have an effect up there. So this was banned. Freon 12 was banned, and we had to find substitutes, which are usually more expensive. But they're chlorofluorocarbons because those types of molecules are very unreactive under normal circumstances in refrigeration units. And they're larger molecules. So they don't tend to split off these free radicals. Oops, that's it. Okay, so that takes care of chapter 12.